Okay, so I think the title is something like Introduction to Derived Deformation Theory. Yes, it's on the course page, so I'll just, if you're needing something to classify your notes, something like derived deformation theory should do it. Right, so I'm going to start off by defining CDGAs, so commutative DG algebras. The idea is that, so in the last talk we saw that you have DG Lie algebras as a generalization of Lie algebras. And there's a completely analogous generalization of commutative algebras, called commutative DG algebras. And the point is that if you've got a DGLA, rather than just defining functors on Artinian algebras or complete local algebras, as we saw last time, you can actually define very natural functors on commutative DG algebras, and that gives you a lot of extra information and all sorts of rich structures. So that's basically what I'm going to be talking about today. So I'll start with just the simple definitions. So, and shout when I can promise I will become illegible at some point. So shout when I do. So a commutative differential graded algebra and whereas the DG Lie algebras, it's conventional to write them as cochain complexes, I've got to write the commutative algebras as chain complexes, and it's might be slightly confusing. It's just I find it easier in my head, partly to do with comparisons with simplician things, and also that in the talks later in the week, it means that the gradings we're using are going to be positive rather than having everything negative. So it's psychologically difficult to work with things concentrated in negative degrees. So, which I'll either write as A or A bullet is, and this is over, so R, which is a commutative Q algebra. If you're an algebraic geometer, you probably want to assume R is just the complex numbers. If you're a differential geometer, you probably want to assume it's just the real numbers. But yeah, the definitions do work over any, well, yeah, over any commutative Q algebra. I suppose the definitions work if beyond characteristic zeros, but things misbehave horribly. Right, so it's a chain complex. Bar modules. So we've got and at this point we've also got negative degrees as well. D squared is 0. This is convention for chain complexes. And so with a graded commutative product. Associative. So this is goes from AM tensor AN to AM plus N. And the gradient commutative associative conditions are saying that BA is -1 to the degree of A times the degree of A of AB. So if M and N are both, if one of M and N is even, then this is just normal commutativity. If they're both odd, you get a minus sign. And then associative is just, you don't have to worry about signs because nothing's passing through anything. And then this is such that D is a derivation. So D of AB, dA times B plus, now because we're passing something of degree 1 through A, we pick up a minus 1 to the degree A. And these are just standard Kazoo signs that you need to ensure that the homological properties of these things behave reasonably well. If you've ever looked at what happens with total complexes, if you didn't have these signs there, things would just go horribly wrong quite quickly. So that's a CDGA, and what we're going to be focusing on. So I suppose we're going to take might as well straight off take a base field K. So we're working over a base field K. Say that an Artinian local CDJ A CDJ, which we can write a direct sum like this, where this so it's got a unique maximal ideal there, such that total dimension is finite and degree 0 thing is nilpotent. In other words, so that last condition is the same as saying that A naught is Artinian. So basically what we're doing is we've got a local Artinian ring in degree 0, and then we've got some finite dimensional stuff in the other degrees. And this condition's ensuring that it's bounded as well, so we've only got finitely many. Yeah.
So can they only live in one direction?
Oh, are you asking if I've got
positive, negative degree, or both ways?
I'm still I'm allowing both at this point. So you know, later on we'll be restricting to just in non-negative degrees, but yeah, for the purposes of what I'm doing today, we're going to have both degrees. And for those who know about this stuff, that's incorporating both derived and stacky information. I'm not expecting that comment to make sense for necessarily anyone, but I'm just saying that now. Right, so that's, and I'm going to write so I'll write DG art for the category. of Tinian local CDJs. And DG plus art, category of the full subcategory in degrees, non-negative degrees, in other words. One where it gets to a naught and then stops. Now, in the first talk, we saw how to associate functors to DGLAs, so functors on the category of Artinian rings, Artinian local rings. But it's not too hard to see that there's a natural way of extending those functors to these bigger categories. Functors associated to so the first thing we do is, we're given DGLA, suppose it and drop the subscripts, but there is a fixed base field floating around here. Pick your favourite field and stick with it, as long as it's not a finite characteristic. So I'm not going to mention the field again, but so given a DGLA over the field you're working over, and some DG Artinian ring, we can then DGLA, give it a name, L. We can now form a new DGLA by tensoring these two things together. So we get a nilpotent DGLA. It's given by total complex. It's a product. So in degree n, this thing, this is a slightly awkward point in that this was a co-chain complex, this is a chain complex. I'm going to make this one a co-chain complex again. So we have direct sum over all integers I. That's a product of ln plus I with MA in degree I. So that's what the underlying vector space is in each case. And then the standard definition of a differential on a total complex. So we have d of, say, v in L, a in A, uv tensor A plus minus 1 to the degree of v. And bracket again, it's you combine the Lie bracket on L with the commutative product on A. So it's just, so if we have tensor A bracketed with B tensor B, find that to be so it's basically UV tensor with A and B, except that we've passed A through V because all sine is minus 1 to the degree of A times the degree of V. So in mind-numbing detail, this is the DGLA we've got when the input is a DGLA and a CDGA. And sort of notice there's nothing really special about DGLAs here. So if you've got any sort of DG algebra and you tensor it with a CDGA, you tend to get another DG algebra of the type you started with. So now, given L, we can now define functor MCL from the category of all DG-Artinian local rings to sets just by sending A. What you do is you form this total DGLA. And then you just take the Mallet-Cut elements as in the first talk. In other words, omega in this is the degree 1 part of the total DGLA such that we have omega plus half the bracket 0. And so in particular, if your input is just an Artinian ring concentrated in degree 0, so if A only has things in degree 0, This just gets back the functor we were looking at last time. And as we saw last time, so this is sort of your generalization of cocycles. So in particular, if your product on n is 0, this gives you cocycles. But we also want some way of generalizing things like coboundaries and cohomology. So I'll give you the two variants of those functors as well. Because what's going to happen is these things parameterize. We're going to parameterize certain types of deformation, but we still need some notion of equivalence between them. So we also define, and this is non-standard notation, but there isn't really notation for it generally. So define this to be exponential of degree 0 term. This thing is a nilpotent algebra. And this whole thing is then it's a nilpotent group, which you get just what happens is it has the same elements as these, or elements are in bijection as the algebra, and it's just so it's things to the form e to the u, where if you want to work out what we call x prime, but you have a multiplication law that involves the lead bracket. So x mu times x v, x for u plus v plus half the lead bracket plus a whole lot of other terms, and this is called the Campbell-Baker-Hausdorff product. If you want so that's and you can look this formula up if you like, and it defines a group. If you want a far more conceptual way of looking at it, what you're doing is you're forming a universal enveloping algebra of this Lie algebra, which is some sort of Hopf algebra, and you're taking the group-like elements in that, or in some completion of that. So it's a way of associating a unipotent group to an nilpotent Lie algebra. So there's that group, and then what happens is that acts on the Markovitch elements. So again, notation varies wildly. I'm going to use star. So if I've got G gauge element, omega a Markovitch element. So roughly speaking, the idea is that this is going to be acting by conjugation. But morally, you often want to think of omega as being omega plus d. So that the formula that works is G omega G inverse is minus. And I'm not going to dwell on the technicalities here, because those of you who are really up to speed with what's going on will have noticed that these individual terms don't live in anything I've defined so far. But basically what happens is you take some universal enveloping algebra in which the multiplication like this makes sense, and then it turns out this does actually get you back in the Lie algebra. And in fact, but, there are various ways of looking at these, but in practice, this acts exactly as you want change of coordinates to, is what's happening. And then, so that's that action. And then we define deformation function. A is going to map to MCLA modulo H. So the thing I call gauge and top there, just like the notation. So let's I think I can just add some that on here. So the simplest sorts of Artinian rings you can look at are the ones where it's just a first order extension of the field. And so in the underlying setting, if you're doing that one dimension, that is where you're looking at so things like k epsilon over epsilon squared. So the simplest Artinian ring, non-trivial Artinian ring. So more generally, this generalizes to cases where this variable lives in a different degree. A plus k epsilon A living in degree A. And squaring to 0, which from this description, it didn't have much choice about where to go. So we just so then what's happening is this is the maximal ideal here, just one copy of k in degree A. Yep.
If I have something like this, doesn't it make the explication of degree minus n?
Sorry, I didn't.
If I have an epsilon n like this, then the multiplication is degree minus n.
So here, so epsilon n squared is so by definition this thing lives in degree 2n. I'm just saying.
Okay, sorry.
I'm defining that to be so. Yeah, this statement is only really telling me anything when n is degree 0. The way I've said, because equivalently you can say it's the free DG algebra on one variable epsilon n, such that epsilon is squares to 0. So there are. This description is very much overkill because I could equivalently have said this is the maximal ideal. Because then even in degree 0, when n is 0, this has nowhere to go. Right, so we've got those things, and now let's look at what these factors give us. So can anyone see what Maron-Cartan will be if I feed it one of these maximal ideals? Anyone? We've only got, but that maximum ideal is only living in degree n. So the only term we pick up is a copy of ln plus 1. So it's omega in ln plus 1. Start there. So that's that. And then, again, the only thing that exists on the right is ln plus 2. So that the bracket's going to be 0 because the multiplication here is 0. So we're just saying so d omega is 0. So in other words, that's isomorphic to Zn plus 1 of that. So when we just look at what happens when we feed the functor one of these rings, our canton is giving us pulse cycles. And if we look at what the deformation functor gives us, and I've been extremely vague about exactly what's going on here, but I think even with the scant detail I've given, you can see that if the bracket is 0, group operation here is just addition, and all that happens here is we end up subtracting a copy of du. So it's just d. So it's just ln acting on this by applying d and then translating. So it's co-kernel d from ln Zn plus 1 L. That's better known as cohomology. So what's happening is this derived deformation functor here, this functor on all these D-Artinian rings knows about all the cohomology of the DGB algebra, not just whereas the underived one can only really see degree 1 and a bit of degree 0 too. And this actually is largely I think this is where a large part of the motivation for studying these started out, because you get the various enumerative invariants, things like invariants, where it starts out working with cases where these DGLOs only lived in degrees 0, 1, and 2. And they get well-behaved enumerative invariants and find that when the DGLAs get bigger, the invariants start misbehaving, and it's exactly because they weren't incorporating this extra data. Basically, because things like Euler characteristics behave well in families, but you need to know all your cohomology to have an Euler characteristic. So that's certainly one of the main motivations why people started looking at these sorts of things. Okay, so we've got these functors, but what on earth do they classify? So we saw last time how these deformation functors tell you about deformation of the algebraic structure you're working with. So if you were starting with an associative ring, you look at the Hochschild complex with the Gerstenhaber bracket, that these things are what give you, so tell you how to deform the multiplication on the vector space, and the analogue of this thing was algebra structures up to isomorphism. So it was change of coordinates, and very similar things happen here. So I'm going to start with the simplest example of all. To take via finite dimensional, actually it doesn't any vector space works. I mean, psychologically, you probably want to think finite dimensional, but so take V a vector space and let L end V, so just in degree 0. So this thing is a ring, and therefore a fortiori a Lie algebra where the bracket is just standard commutator functions. So we've got just something really, really basic. Now, if you feed something like this into the first talk we saw today, what do you get? So what, I've said this is concentrated in degree 0, so what have we got in degree 1? It's just 0. So classically, the Marrow-Canton function of this is 0. And you see what's happened. So the only thing you've got remotely interesting, classically, is the gauge group here. And what's happening there is that's telling you that, because in fact this is the DGLA classifying deformations of V, but vector spaces don't really deform in a very interesting way. so that's what's happening classically. But let's look at what happens when we start feeding in something derived. So we can look at so we'll take A DG Artinian. Local Artinian DG. So let's have a look. So we've got we've worked out the total so degree 1 elements of the total complex of L tensor NA. L only lives in degree 0. And because of the conventions I've got, it would be something in degree -1 there. Sorry, I mean end V. So this is, because that's L north, and that's the only term we've got, such that E omega plus half omega omega is 0 in there. And what's happening is that, well, in fact, because NV is a ring rather than just a Lie algebra, we can rewrite that in terms of the composition product. So we can think of this as omega. Think of that as a map from V to V tensor NA. Or equivalently, V tensor A we can extend linearly, say V tensor A to V tensor A -1 all there, such that it's all there. So we've got that condition there, and then we can rewrite this bracket just comes out as omega composed of omega. Because the sign conventions mean that, or if you like, it's half omega composed of omega plus omega composed of omega, because omega has degree, or has a odd degree, so we're going to plus there rather than minus. So the condition is that that, which is equivalent to saying d plus omega composed of d plus omega is 0, because d omega if you think about the effect of d omega once we're extending things, and I am glossing over details here, but if you do feel like working out the details, you will find that, sorry, and there's this plus the both odd. D composed of omega plus omega composed of d. So what's happening is this equation here is exactly the same as this one here. So what this is classifying is chain complex structures on V tensor A deforming the trivial one. So MCLA is isomorphic to chain complex structures on V tensor A as an A module. Deforming the truth, so I'm sure I have to even have to say. Actually, I don't even have to say deforming trivial, do I? Because and A minus one is a minus one, so it's just so it's. And I think that's that's a good place to stop.
Perfect. So let's thank Jon.
It's going to get very tiring for you. Thanks for the end of every single lecture.
Let's thank Jon for a wonderful talk.